All right, hello everyone. Welcome to section 1.4, matrix equations. This is video 1. All right, so we've seen that if we're given vectors a1, a2 through an, we can create their linear combination, x1, a1 plus x2, a2 plus and so on up to xn, an, where x1 through xn are just real numbers. So this was the topic of the last section. This is vector equations. And then to connect this to matrices, if we collect all of our vectors a1 through an into a matrix, and collect our scalars x1 through xn into a vector x, what we'll write is just that ax is equal to all of this. So we're giving some definition of taking the product of a matrix of these vectors times the vector that we get from all these scalars to give us exactly this linear combination again. x1, a1 plus x2, a2 plus all the way up to xn, an. Okay, so we're defining the product of a matrix and a vector provided their size is correct. And that's just what we're saying here in this definition. If A is an m by n matrix with column vectors a1, a2 up to an, so that means each of these vectors lives in Rm, right? Our matrix is m by n. If we let x be some vector in Rn, then the product, our matrix, of the matrix A and x is just the linear combination of the columns of A with the entries x as weights. So just exactly what we had up here. Okay, and this is all sounding very fancy, but if we write down a concrete example, it becomes not so fancy, more concrete. So let's take a look at an example. Let's look at our matrix, maybe 1, 0, -2, 9, 3, 8, 4, -7, 5, 6. So this is a 2 by 5 matrix. So we better have a 5 by 1 vector here. 0, 1, -1, 2, -2. And what the definition says above is just that we should take each of these column vectors and use these as weights and make that linear combination to get the product of these two things. So I guess we'll go 0, our first entry of our vector, and multiply our first column by that. So 0 times 1, 0, right? 1 times -2, 9, plus -1 times 3, 8, plus 2 times 4, -7, and then plus -2. Whew, we're just going to squeeze this in. 5, 6. Okay, we are, as always, rapidly running out of space. But what'll just happen is what? We're going to get, no contribution from this first term, 0 times whatever. We're going to get a -2, 1 times -2, -1 times 3, so we're going to get a -2 minus 3. Here we're going to get a +8. Here we're going to get a -10. So +8 minus 10. That's the first entry of our 2 by 1 vector. And downstairs, what's going to happen? We should get nothing. 9 minus 8 minus 14 minus 16. So 9 minus 8 minus 14 minus 16. You can check that should be equal to -7, -29, I think is what we're going to get. Okay, so multiplying this matrix for that vector. Okay, let's do some more examples. If we're given vectors v1, v2, v3, of course, we need to put our little arrows to remind ourselves of the vectors. Given these 3 vectors in Rm, we want to write this linear combination. This linear combination as a matrix vector product. Okay, and there's a couple of ways we could do this. We could ignore completely the fact that our vectors are ordered 1, 2, and 3, and just make some matrix out of v1, v3, and v2. And then we know that if we want for them to appear with these weights, we'd better multiply by the vector 2, 4, -3. Boom, done. An alternate solution is the following. Well, you may be naturally inclined to say, okay, well, what we really want is to have the vectors come in order. They must be ordered. That's fine too. I didn't say there's exactly one solution to this problem, and indeed there's more than one. If we want to put our vectors in order, all we need to do is move the weights around so the corresponding weight gets hit to the corresponding vector. So we still want 2 copies of v1. We want -3 copies of v2, and we still want 4 copies of v3. Also a correct answer. They're both matrix vector products that represent the sum. Boom. Okay, what else? More examples. If we want to consider the following linear system, yeah, great to remind ourselves that everything we're doing typically boils down to linear systems of linear equations, same thing. We want to write this as a matrix equation for some specific matrix A and specific vector B. All right. Okay, so we could first collect all of these into one vector and all those into one vector and say, okay, well, we know this is the same thing as saying 2x1 plus x2 minus 3x3, and then x1 minus x2 plus 2x3, 3x1 plus 4x2 plus x3 is equal to 104. And we could keep on breaking this down piece by piece. Yeah, maybe we notice there's this x1 that appears here, and x2 that appears there, and x3 that appears there. So we can write this as the sum of 3 vectors weighted by x1, x2, x3. So this looks like maybe x1, and then what are we doing? We've got a 2, a 1, and a 3. 2, 1, 3, plus x2, and so we've got a 1, a -1, and a 4. 1, -1, 4. And then x3 is coming to us with a -3 plus 2 plus 1. 4. And so it looks like, okay, if these are the columns of a matrix, it looks like what we're getting here should be the corresponding weights. So we're getting back 2, 1, 3, 1, -1, 4, -3, 2, 1. If we hit that matrix with the vector, or by the vector x1, x2, x3, and set that whole thing equal to 104, we're getting back this matrix equation with a specific matrix A and specific vector B. And in particular, the matrix we're getting back here isn't just any old matrix. It is our old friend, the coefficient matrix of our linear system, right? 2, 1, -3, 1, -1, 2, 3, 4, 1. 2, 1, -3, 1, -1, 2, 3, 4, 1. All right. Okay, now we have the following little theorem to help us summarize. Right, so then if A is an m by n matrix with columns A1, A2, 3 up through AN, and B is some vector in Rn, then the matrix equation AX is equal to B has the same solution as the vector equation, which is just the linear combination of the columns of A with weights coming from X, that linear combination being set equal to B. And that has the same solution as the linear system with augmented matrix, where the first n columns are the vectors, the columns of A, and that last augmented column is just your vector B. All right, I'll see y'all in a sec for the next video.